Okay, here we go. Okay, section 3.3. Entitled Polynomial Division. And then we're going to learn a couple of very interesting theorems. The remainder theorem and the factor theorem. All right. Now, if you've had elementary and or intermediate algebra here at Mott Community College, then somewhere along the line, you should have been introduced to long polynomial division. It's not a big fan among students, however, there are moments and times in like calculus 2, whereby you actually have to perform long polynomial division here. So what I'm going to do here is I'm going to use long polynomial division to divide these polynomials here. And then we're going to show you a much more efficient way of dividing a polynomial by a binomial. All right, so here we go. We're going to use our long division bar that we first seen way back in grade school, probably. That's your long division bar. My divisor is 3x plus 2. My dividend is this trinomial here, right here. Now, before we can divide a polynomial by a polynomial, we have to make sure that both the divisor and dividend are written in descending order. That is to say that the degree of each term decreases from left to right. Well, my divisor is in descending order. I have a first degree term and then a 0th degree term. My dividend is a 3rd degree term here, 2nd degree term, and then it drops down to a 0 degree term. Another thing you got to make sure is that you're not missing any powers of your variable in both your divisor and your dividend. I'm not missing any powers of x in my divisor as I go from a first down to a 0 degree term. But I am missing a 1st degree term in between my 2nd degree term and my 0 degree term for my dividend. Because of that, I'm going to have to enter in what's called a placeholder here. This placeholder is extremely important. If you don't put this placeholder in here, then things are not going to line up and you're not going to get the correct quotient, okay? All right, we're ready to begin dividing. I like to, off the side of my paper keep track of my rounds of division. So I'm going to call this round 1 of division here. And I'm going to ask myself, how many times does 3x divide into 6x cubed? Now, to answer that question, feel free to take the 6x cubed and place it over the 3x. And then we can reduce this. So how does this reduce? 3x cubed over 3x. That reduces down to 2 what? 2x squared? All right, so 2x squared is going to be the first term in our quotient. And your author tends to always want to line up like terms in column when performing long division here with polynomials. So I'm going to put the 2x squared above the 5x squared. And there's our first term in our quotient. Okay, we're starting to form our answer here. We now take this 2x squared and multiply it by our divisor. So 2x squared is going to get multiplied by the 3x plus 2. And what's 2x squared times 3x? That gives you 6x cubed. And then 2x squared times 2 gives us 4x squared. And then, ladies and gentlemen, we're going to subtract off this whole polynomial. So make sure you enclose it inside parentheses. We're going to subtract this whole polynomial off. All right, here we go. What's 6x cubed minus itself? 0. So the 6x cubes drop out. What's negative 5x squared subtract 4x squared? Be careful with these signs here. Signs are the biggest, most frequent mistake when performing this division. Negative 5x squared subtract 4x squared is negative 5 minus 4, which is negative 9, so negative 9x squared. And now we drop down the next term, which is 0x, as we set ourselves up for round 2 of division. Now round 2 has arrived. So we ask ourselves to begin round 2 of division. How many times does 3x here divide into negative 9x squared? To answer that question, feel free to put the negative 9x squared over the 3x off to the side of your paper and then reduce this. And how does this reduce? Reduces down to negative 3x. So minus 3x then becomes the next term in my quotient. I'm now going to take the minus 3x and multiply it by my divisor. Negative 3x times 3x nets me negative 9x squared. Negative 3x multiplied by 2 gives me minus 6x. And then what we do is we subtract off the whole polynomial. 9x squared minus itself is 0, and 0x subtract a negative 6x is really 0x plus 6x, which is 6x. And then we drop down to negative 3 as we set ourselves up for round 3 of division. Round 3. We ask ourselves, how many times does 3x divide into 6x? To answer that question, unless you can just visually determine that in your mind, feel free to take the 6x and place it over the 3x and then reduce this. How does that reduce? It reduces down to 2. So plus 2 is the next term in our quotient. 2 now gets multiplied by our divisor. So 2 times 3x is 6x, and 2 times 2 is 4. Subtract off the whole polynomial. So you can see there is a cyclical repetitive nature to this algorithm here. All right, 6x minus 6x is 0. Negative 3 subtract 4 is negative 7. And ladies and gentlemen, we have nothing else to bring down, and therefore our division algorithm has terminated. Another way we can determine that our division algorithm is terminated is because the degree of this polynomial here is less than the degree of our divisor. So we're done. This is called the remainder. And what we normally like to do is bring our remainder up into our quotient, place it over our divisor. So negative 7 is placed over 3x plus 2, and then we're going to add it to the rest of the quotient. And this would be your answer. This entire expression is your answer here. So I put the negative 7, the remainder, over my divisor. All right. Now, a way of checking your answer lies in what is called this division algorithm, which is laid out in your textbook in this section. And this division algorithm says that a polynomial function can be written as the product of the divisor polynomial times the quotient polynomial plus any remainder polynomial. Okay, so in other words, ladies and gentlemen, my polynomial function, which is 6x cubed here, minus 5x squared minus 3, had better be equal to my divisor, which is 3x plus 2, times my quotient, which is 2x squared minus 3x plus 2, plus my remainder, which is a minus 7. Okay, so this would be a way, whoops, sorry about that. This is called the division algorithm, where a polynomial function can be rewritten as the product of a divisor polynomial and a quotient polynomial plus a remainder polynomial. Based on what I've accomplished above there, my polynomial here, 6x cubed minus 5x squared minus 3, can be rewritten as the divisor times the quotient plus the remainder. And if you were to take the time and multiply this binomial by this trinomial, expand it all out, gather together your like terms, and then also combine your constant terms at the end, you would discover that you would get back this polynomial. You would have to. Otherwise, we would have made a mistake up here. All right. And so this division algorithm helps us check our answer, if you will. All right. But normally when we perform long polynomial division, we express our answer like this in its entirety. All right. The quotient added to the remainder over the divisor. Okay. Any questions about this long polynomial division that just occurred here? All right. Well, maybe we can try another one here. All right, we will try to take negative 5 plus x plus 4x squared plus 2x cubed plus 3x to the fourth. And we're going to try to divide this by x squared plus 2. All right, here's your long division bar. And what goes outside and what goes underneath? Where does the x squared plus 2 go? Outside or underneath the division bar?
Outside.
All right, this is our divisor. This is our dividend. But we're noticing some things are not right here. First of all, my divisor is written in descending order, but notice I'm missing a power of x between my second degree term and my 0 degree term. Because of that, a placeholder is necessary to insert in the divisor. So therefore, x squared plus 0x plus 2 must be how we write our divisor. Got to have that placeholder. Notice my dividend is all messed up too. It's not in descending order for one thing. And am I missing any powers of x? I have a 4th degree term, 3rd degree term, 2nd degree term, 1st degree term, 0 degree term. It looks like we're not missing any powers of x, but we need to put this in descending order. All right, we are ready to begin our division here. Round 1. Now, you don't have to do these rounds off to the side of your paper, but it is kind of nice and it helps you to understand what terms, are found in your quotient. For instance, x squared divides into 3x to the fourth how many times? If you cannot visually determine that, feel free to take the 3x to the fourth, place it over x squared, and now by reducing this, you'll have your answer as to what's our first term in our quotient. This reduces it down to 3x squared. So 3x squared is the first term in your quotient. And above what term do I put my 3x squared? Notice we like to keep like terms lined up in columns when we do this long division here. So where would I put the 3x squared above what term in my dividend here?
The 4x squared.
Right above this guy, okay? So 3x squared. And I'm just doing this because your textbook is showing you this method, all right? Most textbooks do keep like terms lined up in columns. Not everyone. I've seen a couple that don't. Some start off by putting a 3x squared over this guy, but I'm just following along with your book because I know we all look at the examples. Now we're going to take 3x squared and we're going to multiply it by the divisor here. And here we go. So 3x squared times x squared is going to be 3x to the fourth. That slides underneath this term. 3x squared times 0x is going to be 0x cubed. And 3x squared times 2 gives me 6x squared. And then we're going to subtract off this whole polynomial. 3x to the fourth minus itself is 0. These drop out. 2x cubed minus 0x cubed is 2x cubed. 4x squared minus 6x squared is minus 2x squared. And then I'm going to drop down the plus x as we set ourselves up for round 2 of division. All right, round 2, we ask ourselves, how many times does x squared divide into 2x cubed? Take the 2x cubed, place it over the x squared, and reduce this. You'll have your answer. This reduces down to just 2x plus 2x, next term in our quotient. Take the 2x, multiply it by your divisor. So 2x times x squared is going to be 2x cubed. 2x squared times 0x is plus a 0x squared. 2x times 2 at the end is plus a 4x. Subtract off the whole polynomial. 2x cubed minus itself goes to 0. Negative 2x squared minus 0x squared is negative 2x squared. X minus 4x is minus 3x. Bring down the negative 5 as we begin round 3 of division. All right, here we go. X squared divides into negative 2x squared. How many times? It'll be negative 2 times. Minus 2 then is the next term in your quotient up here. Take the negative 2, multiply it by your divisor. Here we go. Negative 2 times x squared is negative 2x squared. Negative 2 times 0x is 0x. And negative 2 times 2 is minus 4. Subtract off the whole polynomial. Negative 2x squared minus itself is 0. Negative 3x minus 0x is minus 3x. And -5 subtract the -4 is -5 plus 4, which is -1. Notice we have nothing else to bring down, and notice this resultant polynomial of being of first degree is less than the degree of our divisor. That indicates we are done. The algorithm has terminated. This is your remainder. So what we do is we bring the remainder up, place it over the divisor, and add it to the other terms of our quotient. Now, when you put your divisor down here, you don't have to include the placeholder. No longer necessary. And this is your answer. Okay. That's it. Long polynomial division here. All right. Hopefully you've done this a little bit, maybe in the past. Hopefully, I mean, you should have. If you came through elementary and intermediate algebra, there's no way to get through those courses without ever touching base with long polynomial division a little bit. Okay. All right, ladies and gentlemen, classwork number 1 here. I'm going to give you one to do, okay? All righty, so this is long polynomial division here. All right, classwork 1, today is the 26th day of October. I want you to divide using long polynomial division. So I want you to take 2x squared plus 3x minus 14. And I want you to take that and divide it by x minus 2 using long polynomial division, LPD, short for long polynomial division. All right, go ahead. I'll give you a couple minutes, see if you can hammer that out, and we'll come back and we'll check your results. And then we're going to show you an easier way to divide this or do this problem using something called synthetic division. You are going to love synthetic division. Go ahead and use long polynomial division first on this. All right, did anybody get zero remainder?
Yes.
All right, here's your quotient, 2x plus 7. And our remainder is 0, okay? All right, ladies and gentlemen, this is called long polynomial division. Like I said, it's not a huge hit among you because it does have a lot of steps involved. Although with practice, I mean, it's just a matter of going through all the steps, all right? It does require practice, though, to get all these steps down. There's an easier way to divide a polynomial by a binomial. If we take a polynomial function f of x and divide it by a binomial divisor that looks like this, x minus c, then we can use what is called synthetic division instead of long polynomial division. Synthetic division is much more efficient way to divide a polynomial by a divisor that looks like this. Okay, what we do is, in general, we always divide this number c into the coefficients of f of x. So when you do synthetic division, you're not going to see any variables. All you're going to see is numbers, okay? Whatever this number c is in your divisor, divided in the coefficients of whatever your polynomial function is here, okay? So synthetic division is very compact. What it does is it takes your long polynomial division and it basically compresses it down to one line, compresses it all into one line. So shall we do this problem over again, only divide synthetically? So let's try that. So in other words, we're going to redo this problem over again, but I'm going to use synthetic division this time. And so I have a question for you. Is my binomial divisor of the proper form? Is it of the form of x minus c? The answer is yes. And so what would be my number c here? My number c would be just 2. So I'm going to divide 2 synthetically into the coefficients of this polynomial here. That is to say, I'm going to divide 2 into 2, 3, and negative 14. So here we go. 2 will divide into 2, 3, and negative 14. Notice there's no need to put any placeholders in. If there were, we would have to put like zeros in for placeholders, but we don't have any placeholders necessary here. All right, so we're ready to perform synthetic division. Shall we begin? It's very easy. Synthetic division is fun to do. All you do is you drop this 2 down, and what you do is you multiply, bring the number up, and add. So multiply, bring number up, and add. That's how you do synthetic division in this order here. All right. So 2 times 2 is 4. Bring the number up 4. Bring it up. And now add. 3 plus 4 is 7. Multiply. 2 times 7 is 14. Bring the number up. Add. And you get 0. And we're done. We have just divided this trinomial by that binomial. But how do we interpret our results? Well, look what's happened here. We've taken a second-degree polynomial and we've divided it by a first-degree divisor here. And so what would be the degree of our quotient? Well, when you take a second-degree polynomial and divide it by a first-degree polynomial, the degree of your quotient is going to be of degree 1, of degree 2 minus 1, or degree 1. And so here we go. This is what we leave behind. Here's our quotient. 2x plus 7. Remainder 0. This guy is called your remainder. And we're done. You got to admit, ladies and gentlemen, synthetic division is so much more efficient and quick compared to long polynomial division. All right. Everybody understand what just happened there? So therefore, this is your quotient, 2x plus 7. And that's exactly the same thing we got up here. 2x plus 7 with the 0 remainder. That's called synthetic division. Pretty neat, isn't it? You gotta love it. All right.
Question.
Yeah, go ahead.
Is there going to be cases where we can't use synthetic division?
Yeah, the problem is your divisor has to be a binomial of this form, okay? And that is, you know, somewhat of a limitation, because if you had like x squared minus 2 for your divisor, that's not going to work with synthetic division. All righty. So there is a limitation. but most of the time our divisors of the form of x minus c, especially when we start working with the factor theorem and the rational zero theorem and trying to find all the zeros of a polynomial function, which is right around the bend, okay? So normally we can always use our synthetic division in all cases here. Okay, let's try this one out here. Okay, divide synthetically. I'm going to take negative 10x squared plus 2x cubed minus 5, and I'm going to divide it by x minus 4. Is this a candidate for synthetic division? Is my divisor of the proper form? It sure looks like it. It's of the form of x minus c, okay? My dividend's all messed up, though. It's not in descending order. All right, we're going to have to fix that. Okay, so what do I divide in synthetically? What number do I put out here? It's always my number c. What's my number c in this case? Just positive 4, okay? Now, if your divisor was of the form of x plus 4, then you would be dividing in negative 4. But it's x minus 4. I always tell people, you always divide in the opposite of what sign you see here. If you see the minus sign here, you divide in a positive. If you see a plus sign here, you divide in a negative. All right? Now, what would be the coefficients of our dividend in descending order? And do we need any placeholders? Well, let's see. We have a third degree term whose coefficient is 2. Then we have a second degree term whose coefficient is negative 10. We don't have a first degree term, so we must insert what's called a placeholder. This 0 will be a placeholder for the missing x to the first power term. And then we have our constant term minus 5. Everybody understand how I arrange the coefficients of my dividend? Not only do they have to be in descending order, but you have to insert any necessary placeholders. Now we can begin. Multiply, bring up, add. Here we go. 4 times 2 is 8. Bring the number up, add, and you get negative 2. 4 times negative 2 is negative 8. Bring the number up, add, and you get negative 8. 4 times negative 8, negative 32. Bring the number up, add these together, you get negative 37. And we're done. We have just divided this trinomial by this binomial. Okay, this would be my remainder. And what would be my quotient? Well, I took a third degree polynomial and divided it by a first degree binomial. That means the degree of my quotient must be of degree 3 minus 1 or of the second degree. So here we go. Here's our quotient. 2x squared minus 2x minus 8. And we have this for a remainder. So technically we could say plus a negative 37 placed over our divisor, which is x minus 4. And that's it. Pretty cool, isn't it? It's a lot quicker than long polynomial division. All right, that brings us to our remainder theorem. First of the 2 big theorems in this section. This is called the remainder theorem. It's really interesting what it says. And of course, all theorems have proofs. This is not a proof writing course, but there is a proof to this theorem. If you're interested in viewing that proof, I could dredge it up for you. Just let me know. If a polynomial f of x is divided by a binomial of the form of x minus c, then, ladies and gentlemen, this theorem guarantees that the remainder, after performing that division, is going to be equal to the value of the polynomial function evaluated at c. That's what this remainder theorem guarantees. Now, what's that saying, though? Well, I'll tell you what it's saying. What did use this example back up here. All right, what was my remainder? Negative 37. And I took my polynomial function, which I could call f of x, which is this guy right here, and I divided it by x minus 4. You know what? If I was to evaluate this polynomial function at c, my c being 4, You know what that's going to be equal to? It's going to be equal to the remainder of negative 37. So therefore, if I put 4 into this polynomial function, 4 in here and here, and cranked it out, I would get negative 37. That's what the remainder theorem guarantees. So the function f of x, this polynomial function evaluated at c, is equal to the remainder that you get after doing synthetic division. And you can check that. Negative 10 times 4 raised to the second power is negative 10 times 16, which is negative 160. And 2 times 4 to the third power would be 2 times 64, which is 128. Minus 5. If you were to combine all these, you would get what? I think you would get negative 37. Okay. Pretty neat, huh? So that's what the remainder theorem guarantees. So the remainder theorem. All right, and that's going to become important a little later on here in this lecture. So that's called the remainder theorem. All right. And I'll show you how we can apply that. Let's use the remainder theorem. We're going to use the remainder theorem to evaluate f of negative 2, where f of x, our polynomial function, is x to the 4th plus 4x cubed minus 2x plus 18. Now, one way to do this problem is to put negative 2 in for x everywhere and crank it out. You got your answer. But they want us to do this a different way. They want us to use the remainder theorem to find what f of negative 2 would be. To do that, we're literally going to divide negative 2 into the coefficients of this polynomial function. That's to say we're going to divide negative 2 into 1, 4. We don't have an x squared term. We're missing an x squared term, so we put 0 in for a placeholder for the second degree term. And then we got negative 2 and an 18. Let's now do synthetic division. So negative 2 times 1 is negative 2. Bring the number up, add, you get 2. Negative 2 times 2 is negative 4. Bring the number up, add, you get negative 4. Negative 2 times negative 4 is positive 8. Bring the number up, add, you get 6. Negative 2 times 6 is negative 12. Bring the number up, add, and you get 6. And that's your remainder. So what's the significance of 6? Well, ladies and gentlemen, 6 is equal to f of negative 2. That's your answer. And that's guaranteed by the remainder theorem. So if you were to put negative 2 in here, here, and here, and crank this out, you would get 6. And we're done. All right. Next problem in classwork number, we'll call this classwork 2. I want you to do this one. Using the remainder theorem, I want you to evaluate f of negative 7, where f of x is equal to x to the 4th plus 6x cubed minus 12x squared minus 30x plus 35. So I want you to evaluate this using remainder theorem. The intention is not to have you put negative 7 in for x everywhere and crank this out. I want you to use a remainder theorem to find what f of negative 7 would be. Okay, go ahead and do that. This shouldn't take too long because synthetic division does not take long. All right, so go ahead and crank out what f of negative 7 would be. So what's f of -7 equal to?
Zero.
0. That's what f of -7 is equal to. Everybody get that? So later, what can we conclude? What's the significance of -7 since it sends our function to a value of 0? Here's the significance. X equals -7 is, we say, a 0 of f of x. It's a 0. Or a solution to the equation f of x equals 0. Or an x-intercept of the graph of f of x. That's the significance of what -7 is. -7 is a 0 of the polynomial function f of x, or it is a solution to the equation. If you were to set f of x equal to 0 and solve the equation, the 4th degree equation, it's a solution to the 4th degree equation, or it's an x-intercept of the graph of this 4th degree polynomial function. It's an x-intercept. All right. All right, everybody understand that there? And that leads me now to the next big theorem in this section called the factor theorem. We've seen the remainder theorem. Now there's another very important theorem called the factor theorem, which is going to enable us to do wonderful things in the next section also. So this is called the factor theorem, and it does have a proof just like any theorem. And the factor theorem says this: suppose that we let f of x be a polynomial function if, ladies and gentlemen, f of c is equal to 0, then we say that x equals c is a 0 of f of x. And x minus c is a, you ready for this? It's a factor, is a factor of f of x, guaranteed by this theorem. If c is a 0 of f of x of a polynomial function, then x minus c is a factor of that polynomial. The converse is also true. If x minus c is a factor of f of x, then, ladies and gentlemen, f of c is equal to 0. That's what this factor theorem is all about. So we can determine by synthetic division and the remainder theorem whether a number x equals c qualifies as being a 0 to our polynomial function, and whether x minus c is a factor to our polynomial. So let's ask ourselves this question now: is x minus 3 a factor of f of x equal to x to the 4th minus x cubed minus 11x squared plus 11x plus 12? That's the question we're going to try to answer. Is x minus 3 a factor of this 4th degree polynomial? Boy, there would be no way in elementary or intermediate algebra of determining that. Do you agree? No way. So these theorems are opening up new doors for us now. Well, to figure that out is pretty easy, ladies. I'm synthetically, what do I divide into the coefficients of this polynomial? What do I divide in? I divide in positive 3 into the coefficients. So 1, -1, -11, 11, and 12. Notice no placeholders necessary here. Let's do our synthetic division. 3 times 1 is 3, bring number up and add. You get 2. 3 times 2 is 6, bring number up and add. you get -5. Multiply, 3 times -5 is -15. Bring number up and add, you get -4. 3 times -4 is -12. Bring number up and add, and sure enough, we get a 0 remainder. So I have a question for you, ladies and gentlemen. Is x minus 3 a factor of this polynomial? Yes, it
Yes.
is. It is, because f of 3 is equal to 0, equal to the remainder by the remainder theorem. So since f of 3 equals 0, right, by the factor theorem, then I can conclude that x minus 3 is a factor of f of x. It is a factor. Pretty amazing, huh? Okay. So it is a factor. So in order to be a factor, we had better get a 0 remainder when we divide the constant of the binomial factor synthetically into the coefficients of the polynomial. Let's try another one. Okay. Questions on that? All right, let's try this one. Let's ask ourselves this question. Is x plus 2 a factor of the same polynomial? X to the 4th minus x cubed minus 11x squared plus 11x plus 12. Ladies and gentlemen, I want you to add this on to classwork number 2. I want you to determine for me, is x plus 2 a factor of this polynomial? Go ahead and work that out real quickly. You tell me, is that a factor? Is it a factor? You think that's a factor?
No.
Not a factor. Not a factor because -2 is not a 0. We didn't get a 0 remainder. That's not a factor. All right, let's move on now. Suppose we want to take this polynomial and we want to factor it down. So I want to eventually factor down this 3rd degree polynomial function here. I want to factor it into the product of linear factors. Now this is a 4-term polynomial. There's nothing we can factor out of all 4 terms. I don't think grouping would work on this either. Grouping fails. And so back in elementary and intermediate algebra, there's no way we'd be able to factor this thing. Let me give us a little jump start here, ladies and gentlemen. I'm going to indicate that x equals -5 is a 0 of f of x. That should be more than enough information to completely factor this down. Here we go. So I'm going to divide synthetically -5 into the coefficients of this polynomial function here. And what would I expect from my remainder? What had I better get from my remainder?
0.
0. And if we don't, then this could not be a 0. And this is a contradiction. So we better get 0 remainder. Let's see if we do. Notice no placeholders necessary here. All right, here we go. -5 times 3 is -15. Add, you get 10. -5 times 10 is -50. Add, you get -8. -5 times -8 is 40. Add, and you do get what we expected, a 0 remainder. It has to be a 0 remainder because I told you this is a 0 of my polynomial function f of x. Okay, because this is equal to f of -5. It's a 0. All right, well, ladies and gentlemen, what did I accomplish? I took a third degree polynomial and divided out, well, what did I divide out? If -5 is a 0, then x what? X minus a -5, which is really to say x plus 5 is a what? It has to be a factor. You agree by the factor theorem. So what I accomplished here is I factored out x plus 5. And what did I leave behind? I left behind 3x squared plus 10x minus 8. That's what I left behind. Now, can this trinomial be further factored down using our techniques from elementary or intermediate algebra? 3 times -8 is -24, and 2 factors of -24 that sum up to +10 would be 12 and -2. So it does further factor down. I'm not going to take the time to factor that trinomial down, as we should pretty much know how to factor these types of trinomials, whether you use grouping or trial and error method, ladies and gentlemen. But this trinomial would further factor down into 3x minus 2 times x plus 4. Done. Not only did I completely factor this polynomial down into the product of linear factors, but we could also determine all the zeros of this polynomial. To find all the zeros, you just set f of x equal to 0, which means that you're going to basically set each one of these factors equal to what? 0. So therefore, 1 0 is x equals -5. We known that from the get-go because I told you that was one of the zeros. Another 0 by solving this equation would say x is equal to 2/3. That's another 0, and another 0 would be -4. So we found our 3 zeros to our third degree polynomial function. Those are all the zeros, and we managed to completely factor it all the way down. Okay, so we're starting to do things and be able to do things that we could not do in elementary or intermediate algebra. So we're coming a long ways, ladies and gentlemen. We're really raising the bar now in college algebra here. Any questions about what just happened there?
Yeah, question.
Yeah.
So how does it transfer to x plus 5?
Because the factor theorem says that if x equals c is a 0, then x minus c is a what? A factor. And c is -5, correct? So our factor must be x minus a -5, which is x plus 5. Does that answer your question?
Yes.
That's the factor theorem. Okay. All right, let's move on. Now, what classwork did we leave off with? Number 2?
Yes.
I believe so. All right. Okay. Here we go. So we're going to move now into section 3.4. And this is entitled Zeros of Polynomials And the first thing we're going to run into, ladies and gentlemen, is a very powerful little theorem called the rational zero theorem. The rational zero theorem. This is the third major theorem we're seeing this afternoon here. The rational zero theorem says that if f of x is some nth degree polynomial, and this is a general way of writing an nth degree polynomial. where these A's are just coefficients, okay? And X is the power. Furthermore, to be an nth degree polynomial, we must insist that the leading coefficient, A sub n, cannot be equal to 0. Otherwise, we would not have an nth degree polynomial. Furthermore, ladies and gentlemen, our coefficients have to be integers. With integer coefficients. That means that we're not going to have any fractional or decimal coefficients. Then this theorem says this: if f of x has a rational 0, if it does, it may not, but if it does have a rational 0 meaning that it's a, it could be an integer, it could be a fraction, okay? If this polynomial function has a rational 0, then this 0 must look like this. The 0 must look like P over Q. Where, ladies and gentlemen, P represents factors of the constant term of our polynomial function. Factors of A sub 0, which is the constant term, way at the end. Q must be a factor of the leading coefficient, A sub n, out here. The way I always remembered it is that P comes before Q in the alphabet, so it's just the opposite here. P pertains to the last term. Q pertains to the first coefficient, okay? So P are factors of the constant term, Q are factors of the leading coefficient. Now this rational 0 theorem is not saying that this polynomial function has a rational 0. It's not saying that, it's not guaranteeing that. What it's saying is that if this polynomial function has a rational 0, if it does, it may not, but if it does, it has to be of this form. It has to be of this form where the numerator is a factor of the constant term and the denominator must be a factor of the leading coefficient. That's what the theorem's guaranteeing. That's what it's guaranteeing, okay? Rational 0 theorem. So let's use this rational 0 theorem to, let's try to list all potential. Now, what does that word potential mean? It means that it could be, correct? List all potential rational zeros for this polynomial. Negative 2x to the 5th plus 3x to the 2nd power minus 2x plus 10. So we're going to list all the potential rational zeros that this function may have. Notice the list we're about to build is not saying that they are all going to be zeros of this polynomial function. None of them may be. None of them from our list might actually not be a 0 of this polynomial. But this theorem up here says that if this does have any rational 0, it's got to look like the ones we're about to show you in the list. Okay. So here we go. The zeros have to be of the form of P over Q. P must be factors of the constant term 10 out here. What are factors of 10? Positive negative 1, positive negative 10. Positive negative 2 multiplied by positive negative 5. Those are factors of the positive 10, the constant term at the end there. Divided by Q. Q must be all factors of the leading coefficient, which is negative 2. That would be positive negative 1 times negative positive 2, or we just say positive negative 2 generically. So, ladies and gentlemen, the list of all potential rational zeros for this 5th degree polynomial would be positive negative 1 divided by positive negative 1, which is positive negative 1. Positive negative 2 divided by positive negative 1, which reduces down to positive negative 2. Positive negative 5 divided by positive negative 1, which is positive negative 5. Positive negative 10 divided by positive negative 1, which is positive negative 10. But there's other possibilities. You could have positive negative 1 divided by positive negative 2, which is positive negative 1/2. Positive negative 5 divided by positive negative 2, which is positive negative 5/2. Positive negative 10 divided by positive negative 2 is positive negative 5. We've already accounted for that. We don't have to account for this again. And there you go. This is a list of all potential rational zeros that this fifth degree polynomial may have. So I have a question for you. Does that mean this fifth degree polynomial has all these zeros?
No.
No. In fact, we don't know if any of these are even zeros of this fifth degree polynomial, but I guarantee you, if it does have a rational zero, it must be one of these in the list. It has to be guaranteed by this rational zero theorem up here. So I have another question for you. Could 4 be a zero of this polynomial function? 4.
No.
How do we know that? Because 4 is not in this list. Do you agree? 4 is not in this list. Could 6 be a zero of this polynomial? Nope, you're wasting your time. It's not in this list. If this does have a rational zero, it may not, but if it does, it has to be one of these in this list. It has to be. So how many possibilities do we have here? There's 2, 4, 6, 8, 10, 12 possible rational zeros. Do you agree? That could be rational zeros of this polynomial. All I want to do is just build a list of the potential rational zeros. That's it. We're done with that problem. That's all. Make sense? All right. Obviously, you know where this is going. Not only are we going to want to build a list, but ladies and gentlemen, we're going to want to then try to find all the rational zeros of a polynomial function. So that's where we're headed. Here's the next situation here. Suppose we want to find all of the zeros of this polynomial function, f of x equal to x cubed minus 4x squared plus 3x plus 2. Suppose we want to find all the zeros of this third degree polynomial function here. I got a question for you. Let's say we go back to elementary and intermediate algebra. Could we factor this 4-term polynomial by using the grouping method? Would grouping work here? I don't think grouping would work. Do you agree? It would fail. So back in elementary intermediate algebra, there would be no way of determining, not being able to determine any factors of this, but we would not be able to solve the associated third degree equation if we set this equal to 0. So to find all the zeros of this thing, we would literally set f of x equal to 0, because zeros are another name for x-intercepts. And we always set y, which is called f of x equal to 0, to find x-intercepts. So in order to find all these zeros, we really are having to solve this third degree equation here. But how would we solve it? We can't factor this, can't factor it. See, there's a dead end here. Back in elementary and intermediate algebra, we say we can't do this. But this is college algebra. We have more powerful theorems now to throw at this. Ladies and gentlemen, we're going to use the rational zero theorem first to build a list of potential rational zeros. Let's use that theorem here. So if this has a rational zero, it must be of the form of p over q, where p must be a factor of what? My constant term? What are factors of 2? Positive negative 1 times positive negative 2. The list is short. That's good. That means we don't have as many to try out. And then q is the factors of the leading coefficient, which is positive, which is 1. So factors of 1 would be a positive 1 or a negative 1 times itself. So the list of potential rational zeros have to be positive negative 1 divided by positive negative 1, which is positive negative 1, or positive negative 2 divided by positive negative 1, which is positive negative 2. Here comes the trial and error portion now. Using synthetic division and the remainder theorem, we're going to pick and choose from this list here, and we're going to see which one of these give us a zero remainder when they synthetically divide into the coefficients of this polynomial. Let's try 1 first. We're going to try to divide 1 into the coefficients of this polynomial. So we got 1, negative 4, 3, 2. Notice no placeholders necessary. 1 times 1 is 1. -4 plus 1 is -3. 1 times -3 is -3. 3 plus a -3 is 0. 1 times 0 is 0. 2 plus 0 is 2. No good, because we did not get a 0 remainder. So 1 is not a 0 of this polynomial function. So which one you want to try next? You say maybe -1? Try -1. The good news is synthetic division is fun to perform. So it's not really laborious. -1 times 1 is -1, add -5. -1 times -5 is 5, add, you get 8. -1 times 8 is -8, add, you get -6. No good. -1 is not a 0 of our polynomial. We only have 2 other choices, 2 or -2. If this doesn't have a rational 0, it's got to be one of these. Let's try 2 next. Two times 1, 2, add, -2. 2 times -2, -4, bring the number up, add, you get -1. 2 times -1 is -2, bring the number up, add, and we found 1. We get a 0 remainder. Therefore, 2 is a 0 of this polynomial function. Not only, ladies and gentlemen, is 2 a 0, but x minus 2 must be a what? X minus 2 must be a
Factor.
has to be a factor. So therefore, we can start factoring this thing down. So therefore, we know that f of x must be equal to x minus 2 times what would remain behind. When I factor x minus 2 out of this 3rd degree polynomial, what do I leave behind? What I leave behind is 1 x to what power? I divided out x to the 1st power out of x cubed. What does that leave the power of my quotient to be?
To the 2nd.
Yeah, so it'll be 1x squared minus 2x minus 1. That's what we leave behind. Everybody see that there? So not only we find a 0, we actually started to factor this polynomial down that was impossible to do back in elementary and intermediate algebra. So we're doing things that we could not do back there. Question, can this trinomial itself be further factored down? Are there 2 factors of -1
Yes.
that sum up to -2? Wait a minute, we need 2 factors of -1 that add up to -2. Yeah, I don't know. The only factors of -1 are -1 and 1. You agree? These don't add up to 2, they add up to 0. All right, so we can't further factor that down, but no big deal. Because in our quest to find all the zeros for this polynomial, we would set x minus 2 equal to 0 and get 2. We already found that, but let's set this trinomial equal to 0. Let's set this factor equal to 0. Now we're going to have to solve the quadratic equation. But unfortunately, we cannot solve it via factoring. So to the rescue is the quadratic formula. Let's use that, unless you want to complete the square on this. All right, so x is equal to -b. What's my b? -2. So the opposite of -2 plus or minus the square root of b squared, which is -2 squared, minus 4 times a being 1 and c being -1. And that's all divided by 2 times a being 1. Ladies and gentlemen, we're going to get our other 2 zeros by solving this quadratic formula here. So we got +2 plus or minus the square root of, this is going to be 4. Minus 4 times 1 is -4 times -1 is +4 over 2. Oh, I see why that trinomial could not be factored, because this is not a perfect square here underneath here. So we get x is equal to 2 plus or minus the square root of 8 all over 2. And simplifying the square root of 8, 8 is harboring a perfect square factor of 4. 4 times 2 is 8. So that 4, when you take its square root, can come out as a 2. So this really simplifies down to 2 plus or minus 2 square root of 2 over 2. And then we can reduce 2 over 2, and the 2 over 2 reduces down to 1 plus or minus √2. There's your 2 other zeros. They're nasty. They're not even rational zeros. These are irrational zeros because we got a square root involved. All right, but those are your 2 other zeros. So we found all the zeros. All the zeros are what? X equals 2. That was 1 0. And there's your two other zeros right here. One plus square root of 2 and one minus square root of 2. Not only do we find all the zeros, but watch this. We can now continue to factor this down more completely. Ladies and gentlemen, if 1 plus square root of 2 is a 0, then by the factor theorem, x minus 1 plus the square root of 2 must be a factor. Times, if 1 minus the square root of 2 is a 0, x minus 1 minus the square root of 2 must be a factor. Not only did I find all my zeros, 3 zeros, but I managed to completely factor this thing down into the product of nothing but linear factors. Something that we could not even think of doing back there, like I said, in elementary or intermediate algebra. So really doing things now that we just couldn't do back there, which is pretty cool. I mean, to think that we have all this extra potential now in this course. All right. Does that make sense there? Okay, let's see here. All right. So, let's see, 1, 2, 3, 4, 5. All right, let's maybe we can try another one, or do you want to try this for well, I better work this one out here. Let's try to find all the zeros. This would be pretty steep for a class work here. So we're going to take this horrendously large polynomial here, and we're going to find all of the zeros for it. This is a 1, 2, 3, 4, 5 term polynomial. Wow, we had nothing in our arsenal back in elementary intermediate algebra to factor a 5-termer. We had nothing. I mean, the largest one was a 4-termer where we used grouping. This is a 5-termer, so no hope back in those courses. But this is college algebra. And so, ladies and gentlemen, first of all, what I'm going to do is I'm going to list the potential rational zeros using the rational zero theorem. So here we go. Potential rational zeros must be of the form of P over Q, where P constitutes a factor of the constant term and Q must be a factor of the leading coefficient. So what are factors of -6? Positive -1, positive -6, positive -2, positive -3. Divided by, what are factors of 2, the leading coefficient? Positive -1 times positive -2. So the list of potential rational zeros is going to be all of these divided by positive -1, which is just going to basically give us the same, the numerator back. So these are all potential rational zeros. But we have some other possibilities. Positive -1/2. Positive -2 over positive -2 reduces down to positive -1. We've already accounted for that. Positive -3/2. Positive -6 divided by positive -2 is positive -3. We've already accounted for that. So if this polynomial has any rational zeros, they must come from this list here. All right. Now, just keep this in mind. We have a lot of possible choices here to test out. We have 2, 4, 6, 8, 10, 12 choices. Ladies and gentlemen, always try the simple ones first. Simple ones being positive or -1, positive -2. Don't try the fractions out first. Okay, they're messy. I mean, if you have to, then eventually you're going to have to get into that. Okay, but now always try the simple ones first to try to crack the ice here. All right. All right, well, let's see if we can do that. Let's try positive 1 out. So we're going to divide 1 synthetically into these coefficients here. Notice no placeholders are necessary, as we have all our powers of x. Here we go. 1 times 2 is 2. Bring up, add. 1 times 7 is 7. Bring up, add. Multiply, bring up, add. Multiply, bring up. Doggone it. We don't get a 0 remainder. So 1 is not a 0. Let's try -1. Multiply, bring up, add, multiply, bring up, add, multiply, bring up, add, multiply, bring up. Hey, we found one. Okay, so therefore -1 is a 0. All right, so -1 is a 0. Now, sometimes the first 0 you find might be a repeated 0, which means it may divide in, okay, again, into what you leave behind after performing a first division. So there's times, ladies and gentlemen, when you may want to perform what's called repeated synthetic division using the same 0. So that's what I'm going to do. I'm going to pick up where I left off here. I'm going to try to divide -1 back in here and see if maybe by chance it's a 0 of multiplicity of maybe 2 instead of 1. So let's do this. -1 times 2 is -2. Add, you get 1. -1 times 1 is -1. Add, you get -6. -1 times -6 is 6. And I'll be darned, it looks like -1 is a 0, not once, but twice. It's called repeated synthetic division. -1 is a 0 of multiplicity of 2, we say. By now, what have I accomplished here? By now, ladies and gentlemen, I factored out x minus a -1, which means I factored out x plus 1. How many times? Not once, but twice. So I factored x plus 1 out twice out of this 4th degree polynomial. And what would I leave behind? What would I leave behind? I took a 4th degree and factored out 2 first degrees, which means my degree of my quotient left behind would be of 2nd degree. So I would leave behind 2x squared plus 1x minus 6. That's what I leave behind. Well, look at that. We completely tore this 4th degree polynomial all the way down. Now we ask ourselves, can we further factor this trinomial here? Quick check. 2 times -6 is -12. And are there factors of -12 that sum up to +1, the middle coefficient? After some thought, yes, there are. It's 4 and -3. So this trinomial can and needs to be further factored down. Now, I don't care if you factor down using the trial and error method or the grouping method, ladies and gentlemen, that is entirely up to you. But how would this further factor down? So how would we further factor this guy down here? Let's see here. I could maybe go with let's see here. I'm going to go with a 3, and I'm going to put a -2 here. So this is going to be a minus here, and I think we got it factored there. Let's see if it works. 2x squared minus 4x plus 3x. Oh, that would give me a minus 1x. I needed a plus what, 1x. So what do I got to do here?
Be 2x minus 3 and x plus 2.
We just got to flip the signs, don't we? This has to become a minus, and this guy becomes a plus, and we got it. Okay. So I kind of just used the trial and error method there. So that's going to be minus. This has got to be a plus, and this would have to be a minus. There we go. This is completely factored now. We completely factored that 4th degree polynomial down. Therefore, we can find all the rational zeros just by setting f of x equal to 0, which means we set all these factors equal to 0, solve for all the zeros, and we get x equals -1 of what multiplicity? -1 was a 0 of multiplicity of 2. -1 is a repeated 0. Our other 0 would be found by taking 2x minus 3, setting it equal to 0. We get another 0 as being 3/2. And notice 3/2 is a 0 of multiplicity of 1. And then setting this factor equal to 0. And solving for x, we get x equals -2 of multiplicity of 1. We found all our zeros. Notice the sum of these multiplicities, ladies and gentlemen, add up to the degree of our polynomial. 2 plus 1 plus 1 is 4. And that's exactly what the degree of this polynomial was, 4th degree. That's not just a coincidence. That is actually a guarantee by what's called the fundamental theorem of algebra. Okay. And ladies and gentlemen, the fundamental theorem of algebra basically what it says is this. This is the fundamental theorem of algebra. It says the number of zeros of an nth degree polynomial f of x is exactly n zeros if counted by their multiplicities. That's always true. So the sum of the multiplicities of all the zeros of a polynomial function must always be equal to the degree of the polynomial. So if you solve a fifth degree polynomial equation, the sum of all the zero multiplicities better add up to 5. If you solve a 10th degree polynomial equation, the sum of all the multiplicities better add up to 10. Okay? That's called the fundamental theorem of algebra. There's also another very powerful theorem, ladies and gentlemen. It's called the conjugate pair theorem. This is another theorem. It says this: if f of x is a polynomial with real coefficients, and ladies and gentlemen, if it's true that x equals a plus bi is a complex zero of f of x, then this theorem guarantees automatically that the conjugate a minus bi must also be a zero of the polynomial function. In other words, if your polynomial function has any complex zeros, they always come in conjugate pairs, always. That's guaranteed by this theorem called the conjugate pair theorem. Always true. So in other words, ladies and gentlemen, if 3 plus 2i is a zero of a polynomial, what must also automatically be another zero? What has to be another zero then? If this is a zero, 3 minus 2i also must be a zero of the polynomial. That's guaranteed by this conjugate pair theorem. So complex zeros always come in pairs, always. All right. Okay. Now this is interesting here. Check this out here, ladies and gentlemen. This is a fourth degree polynomial, isn't it? Okay. Now the multiplicity of -1, the zero -1 was 2. So I have a question. Would the graph of this fourth degree polynomial cross through the x-axis at -1 or just touch the x-axis? Do we remember that theorem from the last chapter? Do we remember that theorem? If this is of even multiplicity, would the graph of the function cross through the x-axis at -1 or just touch the x-axis at -1? What do you think? Well, going back in my memory banks, I believe that if a zero is of even multiplicity, the graph will just touch the x-axis, but not actually cross through the x-axis at this x-intercept. This zero is of odd multiplicity, therefore the graph will cross through the x-axis at 1.5. This zero is of odd multiplicity, so the graph of this fourth degree polynomial function will cross through the x-axis at this x-intercept of -2. We could convince ourselves of all this if we just graph this polynomial function. And maybe we could do that, ladies and gentlemen. It's called the Desmos graphing calculator. I'm going to show you that right now to graph this fourth degree polynomial function. Let's go ahead and do that. So I'm going to bring up this calculator, which is called Desmos. It's a beautiful calculator. And I'm just going to type in this fourth degree function. So I got 2x raised to the fourth power. By the way, your power button on your computer, ladies and gentlemen, is the little hat symbol. Okay. This is how you raise a quantity to a power. On your keyboard, you have this little hat symbol. That's how you raise a number to a power. Okay, if you use Desmos calculator. Or we can just use the TI-84 calculator if you want to. All right, I'm going to continue to type in this fourth degree polynomial. So we got plus 5x raised to the third power minus 2x squared minus 11x minus 6. let's convince ourselves. This is the graph of that fourth degree polynomial function. What were the zeros again? -2 was a 0. Notice our graph passes right through the x-axis at -2, as predicted, because it's of odd multiplicity. Notice the graph just touches the x-axis at -1, because that was of even multiplicity. Notice our other 0 out here is 1.5. And notice the graph passes through the x-axis at 3/2 or 1.5. Why? Because it's of odd multiplicity. Isn't that cool? All these theorems are coming together here. Right? Called the Desmos calculator, DESMOS. Just type it in a search engine, Desmos calculator. It'll come up with the web address here. Or maybe I'll just post this link on our Canvas website where you can have some fun and just graph various polynomials here. The beautiful thing about this is you can play around with this. You can adjust these coefficients and just see how the graph is tweaked and all that. It's pretty cool. All right. Makes sense there? Now we'll try this one here. All right, so I'm going to build a list of potential rational zeros here. And they must be of the form of P over Q, where P is a factor of the constant term at the end, and Q is a factor of the leading coefficient. Factors of -3 would be positive -1 times negative +3, which we just, flip the sign, just call it positive -3. That's it. Factors of +1, the leading coefficient would be positive -1 times itself. So the list of potential rational zeros will be positive -1 divided by positive -1, which is positive -1, positive -3 divided by positive -1 is positive -3. So we have 4 of these to check out. All right. So here's what I want you to do. This will be for classwork number 4. Is that correct? I don't frankly care what you call the classwork. I just hope that you can, do these problems that I'm asking you to do. I want you to determine if any of these rational numbers qualify as being the zeros of this polynomial function. So go ahead. You only got 4 to try out synthetically. All right. So go ahead. Divide those 3 synthetically and tell me if any of those are zeros. Go ahead and do that. Well, do any of these work? Are they zeros, any of them? Anybody determine if any of these are zeros?
3.
Okay, 3 works. Let's try 3. I'm going to divide synthetically into the coefficients of this polynomial. So we got 1. Now we're missing a 3rd degree term in here, so we got to put 0 in for a placeholder. Got a 2nd degree term whose coefficient is -2. We don't have a 1st degree term. We're missing that also in between these two, so I have to put another placeholder of 0 in. And then we got our constant term, which
Totally
is
forgot about that.
Oh yeah, a whole bunch of placeholders are necessary. Let's see if 3 works. Multiply, bring up, add. Multiply, bring up, add. Multiply, bring up, add, multiply. You get 63. Yeah, unfortunately, it doesn't.
Yeah, I totally
look right.
forgot about the placeholder.
Yeah, 3 is not a 0. Yeah, placeholders are very important. Try not to forget them because obviously it made a huge difference here. Yeah, 3 is not a 0. In fact, ladies and gentlemen, I don't think any of these are zeros. None of them work. None of them give us a 0 remainder. So how are we going to find all the zeros of this thing? Well, obviously this polynomial does not have any rational zeros, because if it did, they would have to come from this list by the rational zero theorem. So how are we going to find them? Well, let's study this polynomial a little bit closer here. Notice this polynomial or trinomial happens to be quadratic in form. We say that a trinomial is quadratic in form. I didn't say quadratic necessarily. I said quadratic in form if it has this structure: x to the 2n power plus b times x to the n power plus c. We call this a quadratic form trinomial if the deleting degree is twice the degree of the middle term. And notice this 4th degree is indeed twice the degree of the middle term. This is a quadratic form trinomial here. So quadratic form trinomials can be factored. And therefore, I'm searching for a couple of factors of -3 that sum up to -2. And what would they be? What are 2 factors of -3 that add up to -2? Well, that's going to be -3 and 1. And therefore, ladies and gentlemen, this trinomial will factor immediately into not just x, though, but it's got to be x squared minus 3 times x squared plus 1. There's the factorization of that trinomial. Now, to find the zeros, we're literally going to set y, which is really called f of x, equal to 0. Meaning we set each of these factors equal to 0, as we would set this whole equation equal to 0. And to solve for x, we would have to set these variable factors equal to 0 and then solve each of these quadratic equations. Solving this quadratic equation first by using the square root property, we would add 3 to both sides. And then I would take the square root of both sides of my equation, keeping in mind that I take the plus or minus square root of the number sign. And so we're going to get 2 zeros, positive or negative square root of 3. Solving this quadratic equation for x by subtracting 1 from both sides. Isolating the squared term, now taking the square root of both sides of our equation. Don't forget it's the plus or minus square root of the number side. And x is equal to what? What's the square root of -1 equal to? Do we remember? By definition, it's what? Equal to? What's the square root of -1 equal to?
I.
I. Recall that I, the pure imaginary unit, is equal to the square root of -1 by definition. So our other 2 zeros happen to be complex conjugate zeros. One is positive I and the other one is negative I. Why must these come in pairs? Why do they have to come in pairs? By what theorem was that? Do you remember the name of that theorem? The conjugate pair theorem, agree? Guarantees that if you got any non-real zeros, they must always come in conjugate pairs. All right. Furthermore, ladies and gentlemen, I have a question for you. What was the multiplicity of these zeros? What's the multiplicity of positive square root of 3? Well, that's just going to be a multiplicity of 1. What's the multiplicity of the other 0? Negative square root of 3. That would also be multiplicity of 1. What's the multiplicity of positive I? That's multiplicity of 1. What's the multiplicity of the other 0, which is negative I? Multiplicity of 1. If you add these multiplicities together, do they sum up to the degree of the polynomial? 1 plus 1 plus 1 plus 1 is 4. We had a 4th degree polynomial. The fundamental theorem of algebra has been confirmed. The sum of the multiplicities of all the zeros of a polynomial function always add up to the degree of the polynomial. Furthermore, if I was to graph this 4th degree polynomial, which I don't think I'm going to do that right here, but would my graph cross through or just touch the x-axis at square root of 3, which is an irrational number, by the way. It's approximately about 1.7. So would my graph cross through or just touch the x-axis at about 1.7? Well, that's of odd multiplicity. So that means the graph would actually cross through the x-axis here. The graph would also cross through the x-axis at about negative 1.7, this other x-intercept, or 0. You would not see these represented as x-intercept in the real plane because these are not real numbers, okay? So it's going to appear that when you graph this 4th degree polynomial, the graph would only have 2 x-intercepts, namely these. But it really does have 4 zeros, ladies and gentlemen, just that 2 of them are non-real. Furthermore, according to the far right, far left end behavior theorem, remember that back in chapter 2? This is an even degree polynomial where the leading coefficient is positive. So that means the left behavior of the graph and the rightmost behavior of the graph would have, in both cases, have this graph going upwards. Do you agree? Upwards. And my graph has to cross through at what? Negative square root of 3? Has to turn around somewhere in here because it's got to go through the other x-intercept of positive square root of 3. So these would be your x-intercepts, positive square root of 3 and negative square root of 3. Those are your x-intercepts. Those are the only ones you're going to see. But don't get me wrong, there are 4 zeros to this polynomial. It's just that the other 2, like I said, are non-real. They're imaginary zeros. Okay? That's why you only see 2 x-intercepts in the real plane. Is this making sense here? All right, I'm going to wrap up this session with one more problem, and that's it. Suppose that I am given this 4th degree polynomial. This is a 5-term polynomial. And suppose that I tell you that 3 minus 4i is a 0. Based on that, ladies and gentlemen, I want us to find all of the remaining zeros. All right. Now, one of the zeros we can just basically just read right off. What has to be another 0? Guaranteed. What has to be another 0?
Isn't it 3 plus 4i?
That's right. It would be the complex conjugate of 3 minus 4i. By the conjugate pair theorem, these imaginary or complex zeros always come in pairs, conjugate pairs. So another 0 has to be guaranteed 3 plus 4i. So we have 2 zeros. Right off the bat, we found 2 zeros. So if I divide these synthetically into the coefficients of this 4th degree polynomial, I better get 0 remainders. Agree? Let's do that. Let's divide 3 plus 4i in first. Word of caution. When you divide complex numbers in the coefficients of a polynomial, you're going to need a little bit of lateral space. So make sure you spread this out a little bit, these coefficients. 1, negative 6, 28, negative 18, and then 75. Let's begin our division, our synthetic division. So 3 plus 4i times 1 is 3 plus 4i. Now we add these together. Remember, when you add or subtract complex numbers, you can only add or subtract the real parts and the imaginary parts separately. What's negative 6 plus 3? Negative 3. And now I'm going to have to multiply 3 plus 4i by negative 3 plus 4i. To do that, you might want to, work that out off to the side on your paper. So, I'll do that on a separate piece of paper. I don't want to clutter this up. So here's my workspace here. I'm going to take 3 plus 4i, and I'm going to have to kind of multiply it out with negative 3 plus 4i, kind of using our FOIL algorithm that we use for multiplying binomials together. So here we go. We got 3 times negative 3, negative 9. 3 times 4i plus 12i. 4i times negative 3 minus 12i. And then we're going to take 4i times 4i, which is going to give me 16i squared. But what's I squared? Recall I squared is negative 1. Therefore, combining my two middle-like radicals, I have negative 9. Oh, what happens here, the 12i's? Let me make sure I did this right here. Yeah, well, they drop out, don't they? Okay, well, they did drop out. So I'm left with negative 9 plus 16 times I squared, but I squared is negative 1. And so therefore, this is negative 9 minus 16, which is negative 25. So therefore, when I multiply 3 plus 4i by negative 3 plus 4i, I'm left with negative 25. So let's bring the negative 25 back to our synthetic division here. Add these together. You get 3. Now what's 3 plus 4i times 3? What's 3 times 3? 9. And 3 times 4i plus 12i. Add. Negative 18 plus 9 plus 12i. Negative 18 plus 9 is negative 9 plus 12i. And then we're going to multiply these together. What had these better multiplied together to give us? What do they got to give us? They have to give us what? They better give us negative 75, or else we made a mistake somewhere. Because remember, this is a 0. All right, so let's just see 3 plus 4i. Let's convince ourselves. Multiplied by negative 9 plus 12i. Does it give me negative 75? Here we go, foiling this out. 3 times negative 9 is negative 27. 3 times 12i is 36i. 4i times negative 9 is minus 36i. 4i times 12i is going to be 48i squared. Two middle terms drop again. Interesting. So we have negative 27 plus 48 times I squared being negative 1. And we got negative 27 minus 48. And what do these add up to? Negative 75. Exactly what we thought they had to add up to. Okay. And so we do get a 0 remainder. And we have to get a 0 remainder because we were told this is a 0. Okay. Now I'm going to pick up where I left off. If 3 plus 4i is a 0, 3 minus 4i is a 0. So I'm going to use repeated synthetic division now. I'm going to pick up where I left off here. And I'm now going to divide in 3 minus 4i into what remains after performing the first division. 3 minus 4i times 1 is going to be 3 minus 4i. But what do these add up to? These add up to 0, don't they? This time 0 is going to be 0. 3 plus 0 is 3. Now what's 3 minus 4i times 3? 3 times 3 is 9. 3 times negative 4i is minus 12i. Add these together, and we do get exactly what we suspected. We should get a 0 remainder because this is also a 0. By now, I've got my polynomial down from a 4th degree all the way down to a what degree? What degree remains after having performed 2 divisions? I got it down to a 2nd degree polynomial. So what remains is 1x squared plus 0x plus 3. All right, so ladies and gentlemen, what have we accomplished? What we've accomplished is quite a bit here. We've taken this 4th degree polynomial and we found 2 zeros for it. Not only do we have 2 zeros, but we also found 2 factors. Because if 3 plus 4i is a 0, by the factor theorem, x minus 3 plus 4i has to be a factor. And if 3 minus 4i is a 0, by the factor theorem, x minus 3 minus 4i has to be a factor. And what we leave behind is x squared plus 3. So look at that. We've torn this all the way down. We factored that 4th degree polynomial down into this. Now to find the remaining zeros here, we just set the last factor equal to 0 and solve for the 2 remaining zeros, which means we have to solve this quadratic equation now for x to get our 2 remaining zeros. To do so, I subtract 3 from both sides, and then I'll take the square root of both sides. And that implies that x is equal to positive or negative the square root of negative 3, which means we're going to have positive or negative I times the square root of 3. There's your other 2 zeros. They happen to be complex conjugate zeros. So we're done. And so therefore, all of our zeros are going to be what? Well, we found our zeros to be 3 plus or minus 4i. There's 2 of our zeros. And the other 2 zeros happen to be plus or minus I square root of 3. So we happen to have all complex zeros here. They're all complex zeros. And notice they come in conjugate pairs. And notice they all occur with multiplicity of 1. So we got 1, 2, 3, 4 zeros. And by the fundamental theorem of algebra, the sum of those multiplicities better be equal to the degree of the polynomial. And that's exactly what it is, a 4th degree polynomial. Furthermore, not only do we have all our zeros, but we can completely factor f of x down now into x minus 3 plus 4i times x minus 3 minus 4i times x minus square root of 3i times x plus square root of 3i. So we've taken that 4th degree polynomial and completely factored it down into the product of nothing but linear factors. If you were to take the time and multiply all this back out, gather together your like terms and terms would cancel, you would get back, guaranteed, this 4th degree polynomial. All right, so ladies and gentlemen, we covered a tremendous amount of ground today with a whole bunch of theorems that enable us to do things that were only, dreamed of about back in elementary and intermediate algebra. So we've come a long ways in being able to find not only all the zeros of a polynomial, but also completely factor a polynomial down into linear factors. I have a question for you. If I was to take the time to graph this 4th degree polynomial, would I see any x-intercepts in the plane? Would this graph cross the x-axis anywhere? Yes or no? Would it cross the x-axis anywhere? Would it even touch the x-axis anywhere? The answer is absolutely what? Not anywhere, because all of our zeros were complex or imaginary zeros, and you don't see complex or imaginary intercepts in the real plane. So if you were to graph this 4th degree polynomial, and you can take the time to do that using Desmos or your TI-84, graphing this, you would discover that this graph does not even touch or cross the x-axis anywhere. And yet it still has 4 zeros. It's just that the zeros are all complex zeros, okay? They're all complex. All right, that is it, ladies and gentlemen. Hopefully you enjoyed this little get together here, and